All right, let's dive into the world of systems programming. We're going to look at a story of evolution, really. It's a tale of three absolutely brilliant languages, C, C++, and Rust, and how each one tried to answer the same fundamental question.
And this is that question. I mean, for decades, this has been the ultimate balancing act for developers. You want your code to be lightning fast, you want total control over the hardware, right? But you also need to build software that's reliable, secure, and doesn't just crash or leave you wide open to attack. This is the challenge that connects all three of these languages.
So, to really get this, we've got to start at the beginning. The whole world of systems programming is about getting close to the metal. Writing the software that directly talks to and manages the computer's hardware. We're talking about operating systems, device drivers, the very foundation that everything else is built on.
This quest for control, that's what started it all. Programmers needed a tool that was way more efficient and powerful than writing an assembly language, but still structured enough to build really complex systems. And that brings us to the first hero of our story.
Meet C. Born way back in the early 1970s, C is like a master craftsman's chisel. It's incredibly precise, unbelievably powerful, and has absolutely no safety guards. It was built to give programmers direct, unfiltered access to the machine.
And this really captures C's whole philosophy. It's procedural, so everything is organized into functions. It gives you direct memory access through things called pointers. You can literally point to a spot in memory and say, put my data right there. It has almost no runtime overhead, meaning there's no bulky garbage collector slowing things down. And it's super portable, which is exactly why it became the bedrock for operating systems like Unix and Linux.
But here's the deal with C, and it's a huge one. That power comes at a price. See, C trusts you, the programmer, completely. You have total control, which is great, but that means you're also responsible for everything. You have to manually ask for memory and then remember to give it back. One tiny mistake, and you get memory leaks, random crashes, or even worse, security holes like buffer overflows. With C, you hold all the power, but you also hold all the risk. So as software got bigger and more complicated, trying to manage everything by hand in C became a massive headache. And so in the 80s, C++ arrived on the scene. Think of it as evolving that simple chisel into a sophisticated modern multi-tool. It was designed to help manage all that complexity while holding on to all of C's original power. And you can see exactly how it was built. It started with C right at its core, so you don't lose any of that raw speed. But then it layered on these powerful new concepts. It added classes for object-oriented programming, so you could group your data and functions together logically. It added templates so you could write flexible, reusable code. And it introduced a totally game-changing philosophy for managing resources. That philosophy is called RAII, and it's a cornerstone of modern C++. The idea is simple but just brilliant. You tie a resource, like a chunk of memory, to an object. When the object gets created, the memory is acquired. And when that object is destroyed, like when it goes out of scope at the end of a function, its destructor automatically runs and frees the memory for you. It's like the cleanup code is baked right into the object itself. This is what gives you automatic, predictable cleanup without the performance hit of a garbage collector. It's the magic behind things like smart pointers. But you probably saw this coming. C++ has its own trade-off. It gives you these incredible abstractions that let you build massive, complex systems. The whole idea is zero-cost abstractions, meaning you shouldn't pay a performance penalty for using them. But in exchange for all that power, C++ is one of the most complex languages ever made. The learning curve is steep, and this is the real kicker. You can still drop down to the C level and make all the same old memory mistakes if you're not careful.
So for decades, the choice was between C's raw power and C++'s complex abstractions, and both kind of left the door open for those really nasty memory bugs. And this brings us to Rust. It's a modern language designed to solve this problem once and for all. Think of it like a power tool that has an intelligent, built-in safety system that just will not let you hurt yourself.
This right here, this is the problem Rust was born to solve. And we're not talking about minor glitches. Memory safety bugs are the root cause of some of the most catastrophic security vulnerabilities and system crashes out there. The creators of Rust basically asked, what if we could make the compiler prevent these bugs from ever even happening in the first place? And the answer is Rust's secret sauce, the borrow checker. It's this amazing feature built right into the compiler. It enforces a very strict but simple set of rules about how your code can access data. The main rule is this. At any given time, you can have either one part of your code allowed to change the data, that's a mutable reference, or you can have any number of parts just reading the data,
Those are immutable references. But you can never, ever have both at the same time. It just prevents that entire category of chaos.
And the payoff for following these rules is just enormous. Entire classes of bugs that have plagued C and C++ developers for half a century are simply impossible in safe Rust. Null pointer errors? Gone. Eliminated by a system that forces you to handle the case where a value might be missing. Dangling pointers? The compiler's lifetime checks make them impossible. Data races, those really tricky bugs in concurrent code? Prevented by design. It's a genuine paradigm shift.
And this quote just nails it. This is the promise Rust delivers on. You get the memory safety guarantees you'd normally only find in slower, garbage-collected languages, but you get it with the bare metal performance of C and C++. It really is designed to be the best of both worlds.
So, C, C++, Rust, which one is the best? Well, the real answer is that this was never about finding a winner. It's about choosing the right tool from the toolbox for the specific job you have to do.
This table gives us a fantastic summary. C's philosophy is trust the programmer. You use it when you need absolute simplicity and direct control, perfect for things like OS kernels or tiny embedded devices. C++ is all about zero-cost abstractions. It excels when you're building huge, complex systems and need all that power and flexibility, like in game engines or web browsers. And Rust's philosophy is safety and speed. It shines when correctness and security are non-negotiable, making it ideal for things like cloud services or critical command line tools.
And that leaves us with one final thought. From the simple, powerful chisel of C to the complex multi-tool of C++ to the safety-first design of Rust, the story of systems programming is really a story of evolving trade-offs. And as our world relies more and more on software, the big question for the next generation of developers is, which of these values, simplicity, abstraction, or safety, is going to matter most in the future?